Good afternoon, everybody. My name is Gert-Jan Scheppers, as introduced by Maas, and I'm very glad that we have now the opportunity to present to you the new release of Diana 9.5. We will discuss some new features and introduce you in the workflow of this new version. But before doing this, I want to make a step back and look at you at the different interfaces that we have presented to you during the last years. Our traditional user interface is the iDiana pre-post processor, which has scripting functionality, covers almost full Diana functionality, but it is not up-to-date user interface. It's a little bit outdated, and that's why a number of years ago, already 6-7 years ago, we have introduced an alternative pre-post processor to you, which is the Midas FX for Diana pre-post processor, which has integrated geometrical tools for setting up CAD models and very powerful mesh engines. And from both preprocessors, the model can be imported in the Diana environment, where it can be prepared for analysis by Diana, and results are prepared which can be visualized in either the iDiana post processor or the FX Plus post processor. We want to combine in the near future the strong features, the strong properties of both environments in a new environment, which the first version we are going to show to you today. This is an integrated environment which allows scripting, which allows up-to-date geometrical capabilities, meshing procedures will be added later. But our focus is that our purpose is that we want to set up this general graphical environment for Diana in a way that we can easily make it suitable for different applications. So we will have attention for international design codes, integrate design codes, but also more customize it for the structural engineer, the geotechnical engineer, other type of applications. And of course we want to do this that it is easy to use. So what we are going to present to you is the first version of this new graphical environment, which we will make available to you as a new mesh editor in Diana 9.5. After we have done this, we will also give you an overview of new material models, new element types, new analysis procedures, specific design functionalities, geotechnical functionalities, and licensing that will become available in this new Diana version. So let's start with this new mesh editor. In this sheet you see the traditional steps or phases in doing a finite element analysis, starting with the model definition, followed by the finite element analysis itself, and then the post-processing. And as I explained already to you, we have different routes. We maintain in Diana 9.5 also the traditional iDiana route for pre-processing and post-processing, and of course the FX Plus route in which the user can set up his model and do also post-processing in FX Plus. And both environments result in text files in which the mesh is converted to Diana for analysis. That is the traditional .dot file or the FXD file, but we also fully support Nastran import. These text format models are automatically integrated in the new graphical mesh editor, a new graphical user interface in which the user can modify his model, for example, by group definition, by in a graphical way defining supports or loadings, update the material definition or completely set up the material definition, set up the analysis control, run the analysis, and we also offer in the same environment basic functionalities for post-processing. This mesh editor covers the full Diana analysis functionalities. So all material models, all analysis settings can be defined in this environment. In the near future, we will extend this same graphical user interface with more pre- and post-processing functionalities. So when we look to the new graphical user interface of the mesh editor, you see a screenshot here from this, and you recognize on the left hand side here a harmonica tree in which the different aspects of the model can be reviewed or defined. Below here we have a property box. If you select, for example, a defined material, you see the material properties that are defined for this item. Or we have an output dialog box in which the logging from the analysis is defined. You can distinguish here between errors or warnings or messages. As explained, this new environment also supports batch control. So here we have a Python command console in which all the operations can be are covered. For example, setting up material models, or setting up analysis control, or creating a sequence of pictures are locked in a file and can be controlled in a Python type way. Python is a programming language, so in addition to the functionality that we had in iDiana, we can now also define conditions or loops in which we do certain operations. We have a result tree that you see here, which for different analysis that have been defined, we can select result items. We have analysis command tree which we can set analysis settings. We have a graphical window model. The mesh can be displayed with results or without results. We have a menu bar here at the top, and we have different icons. So the functionality in this version of the mesh editor in Diana 9.5 covers the following. We can import models from the existing formats from external preprocessors, always in mesh level. We can view the mesh, we can create groups, we can add properties like materials, geometries, and data settings. We can create support sets and nodal loads. We can define materials through classes, so through dialogues, not any longer restricted to the individual keywords, but the user selects a class of for the material definition, and then a dialog appears in which the required parameters can be defined. Other loads can be viewed so that the user can check them easily. We can set up the analysis settings, for example, what type of analysis you do, or if you do a phased construction analysis in a certain construction phase, which parts of the models are activated, or which solution procedures you want to do. We can check these settings in graphical way. We can run the analysis. We can create contour plots of results in a deformed mesh or undeformed mesh, and we can display vector plots. And of course, everything that all these operations can be locked in a graphical way, or we can be locked and replayed through scripting. So now Mas will give you a short demo on how the workflow of this new Diana 9.5 will work in combination with FX for the pre-post processor.
Thank you, Herdian. The general workflow for Diana 9.5 starts from modeling aspect of that. We use FXT to generate our modeling part. You can incorporate your geometry through the import function, which are based on CAD drawings, or other types of import functions like step or format IGS BREP. For this particular case, before I start this live demo, I would like to extend our great appreciation to Professor Armin Hadrovic from University of Mostar in Bosnia, because he allowed us to use one of his landmark projects for this showcase. He's using this project for assessment of the safety of this structure. It's very complex, but for this particular demo, I'm going to show you the general aspect, how it looks like in terms of setting up the model. But the detailed nonlinear analysis, fully solid structure interaction, fluid structure interaction, will be published and presented later on in one of the Geotechnical webinars. So this is the general model. It's an arch dam with the reservoir behind of that. The next step after having your geometry is to assign mesh set for this geometry. So I hide my model, show the mesh model. In this particular case, you can see them under the works tree. All the corresponding parts related to the model, including foundation, the cantilever parts of the dam body. You can see each based on individual segment, different interfaces, and the upper passage. It's a bridge on top, and the interfaces between the cantilevers and foundation. Also reservoir and corresponding interface to transfer all the effect of reservoir to dam body. So all these mesh sets have been assigned and defined in FXT. Moreover, here you can deal with some basic material properties, or you can proceed with defining your loads and boundary conditions. And if you are dealing with some sort of variation, depends on the time or geometry, you can assign the corresponding function to those loads and boundary conditions. The next step after having your model mesh in FXT is transferring that to the new environment is Mesh Edit. So you easily transfer it through the analysis and edit model with Dana Mesh Editor. You transfer the model to this new environment, and as Herdian already mentioned, this consists of main menu, several standard tools and icons in terms of new, open, save, do, undo, different display options in the pre- and post-processing analysis setup, general working window, and the model window. The model window consists of several sections. Each section consists of different control options for user, for instance, from the unit part. Then we go to the mesh model. As we move through these segments, you can see the corresponding highlighted mesh sets in the working window. We have different view and options for or operation for the loads, boundary conditions, support constraints, elements type, and material. One of the important developments that we have done here in Mesh Edit is creation of the new material model throughout one interactive environment. So you can easily define your material property, depends on the class of material that we have defined. The first level is class of material consisting of concrete and masonry, steel, concrete for design codes, steel based on the design code, soil and rock, interface, and reinforcement elements. So we select one of these classes, And based on the corresponding class, program automatically makes series of constitutive models associated to that class available to user. So for instance, for sand and for soil and rock, there are kind of all these available conventional constitutive models that are in this drop list. You can see them. For this particular case, for instance, I can use modified Morclomb. Based on the type of analysis that you want to consider, you can add and select additional parameters. For instance, if you want to consider the effect of thermal, creep and shrinkage, groundwater flow, initialization. So based on those, you can check on or check off one of these options. After clicking on OK, here you can see the compulsory or all the necessary input fields for this constitutive model. You can easily open them based on the different level and input the corresponding parameters right away into these dialog boxes. Moreover, you can deal and customize your element data. It refers to the integration scheme. In terms of number of gauge points, you can easily define them in the property windows. As Herdian already mentioned, here we have Command Console for customizing your analysis setup in Python language. This could be, say, in the process of variation or introduction of the new material model, or variation of them, setting up the model, changing the loads, boundary conditions, setting up the analysis, and also customizing your output in terms of the contour plot or specific type of tabular output. On the right-hand side, this is our analysis dialog box. This is very intuitive. You can easily create a new analysis case. Based on the type of analysis case, you can have access to various type of analysis that we have. In Dana, as you know, we have many type of analysis features and capabilities. You can select one, and based on the corresponding features and options, you can go through them and customize your analysis setup. For this particular case, I just defined simple eigenvalue analysis with 30 intervals, and you can perform the analysis. For ease of use, I just pass the results in back to FXT, and that's mainly because of the different animation that we can get. So after performing the results, you come back to FX, and here in the post-processing, you can see the variation of the results based on the eigenvalue analysis. These are the average deformation based on various eigenfrequencies. So this was kind of general workflow. This is what you, as a user, for based on FXT and Dana, you may need to consider for your operation. So I hand over the microphone to Dr. Scruthers.
Thank you, Mas. So we think that with this demo you have an insight in the new workflow in Diana 9.5. And we hope that you agree with us that this gives already much more integrated approach, everything in more or less the same user interface, very graphical oriented than you maybe used from earlier versions. There are a lot of different aspects in this new graphical user interface, and the scope of this seminar is not so suitable to touch that all, but we will certainly address that in the near future in following seminar. In the second part of this seminar, we want to go, as announced, through some of the new analysis functionalities that come available in Diana 9.5. And Mas indicated already briefly that one of the new features with respect to material models that we introduce in 9.5 is the input of material models with reference to international design codes. You see here the material class definition as we have in the MESH edit. You can go to concrete design codes, and there we offer the wide variety of different design codes. When we choose, for example, the Eurocode, we can just select a class, concrete class, according to the Eurocode, and all the properties for the selected aspects that we want to consider, either cracking or creep or elasticity, plasticity, shrinkage, are defined automatically with reference to this design code. Apart from Eurocode, we offer also the SAP-VIP codes, the 1990 and the 2010, some American codes as ACI, ASHTO, Japanese codes, Korean codes, and also Dutch codes. We are a Dutch company, so there are also some other material new developments. For example, Tresca and Fomesis plasticity are traditional material models, and the user always, for the hardening, need to define the properties in terms of a plastic strain and a yield stress development in a so-called Hardia diagram. But this is not so comfortable for engineers, because material models usually, material characteristics usually are defined in terms of total strain and stress development, or total strain and reduction of stiffness. So we have made another hardening definition possibility available, which we call here the total strain stiffness ratio diagram, in which the user can define the total strain and the stiffness ratio. In fact, it is the same information, but it is a different way of defining the same information. We have extended the Fomesis and Drucker-Prager plasticity models with kinematic hardening. So what is kinematic hardening? Kinematic hardening means that we create a kind of shift in the loading-unloading cycle of these plasticity models. And this is available for all type of elements. So we need to define, depending on the element type, a stress shift. For a truss and cable element, this is only a one-dimensional value, but for a three-dimensional model, three-dimensional element type, this requires more input. So new bond slip relations for interface elements for the connection of reinforcement bars to concrete. This is a Japanese model defined by Professor Shima et al. Interface elements, surface interface elements, we allow the user now to define orthotropic shear properties, so two stiffness, elastic stiffness values in the different tangential directions. We have new models for cyclic behavior of steel reinforcements. This is an American model, Dot Restrepo model, which is characterized by a yield plateau, followed by secondary hardening, but also typical unloading, reloading cycles which make use of Bauschinger curve. And you see all these models can be input through the material dialogues as shown before. A new user-supplied subroutine for uniaxial springs, relatively simple elements, but sometimes we have had the request from users that they want to make rather complex strain history dependent relations or user supplied characteristics for relations between 2 points in the model, and this user supplied subroutine for springs can be used either for translational springs or for rotational springs, gives the optimum flexibility for a user to define these kind of characteristics. We have extended the crack models, both total strain crack models as Meikawa models, as discrete cracking, and also in stiffness, both in nonlinear analysis as stiffness adaptation analysis, with GCI curves for softening and tension stiffening. That's especially for our Japanese users. Some more shear retention models have been added, and the request for more specific shear retention models comes especially because the design codes in several countries are developed and getting more popularity now, and getting also more attention for nonlinear aspects. Difficult thing is that different regions have their own opinions for how to choose the characteristics, for example, for shear retention, and we want to offer all the solutions that are promoted or in the different design codes in the Diana program. Meikawa is a leading model for reinforced concrete in Japan, also in other parts of the world. So far we have offered a special Meikawa concrete model in Diana, but we have in Diana 9.5 we are extending also the established total strain crack model with a compression curve as defined by Professor Meikawa, which is the Meikawa cracked concrete model. And typical of this total strain compression curve is that it will be used in combination with nonlinear unloading reloading curves automatically. So in the traditional total strain crack model we always have secant unloading and reloading, but when we define a total strain crack model combination with Meikawa compression curve, the Meikawa unloading reloading will be used automatically. The modified Takeda model is a model that can be used in combination with beam elements. For example, the two-dimensional class 1 beam elements, which is a direct integrated beam element. But here we have a nonlinear relation for the bending moment curvature, which is defined by a number of bending points. For example, the first bending point for the initiation of the cracking of concrete, when the stiffness, the bending stiffness is reduced with a certain factor, and a second bending point which is characterized by the onset of yielding of reinforcement. And the nice thing of this model is that there are pretty advanced unloading, reloading cycles integrated in the model. 7 different cases defined. For details I refer to the manual. Here you see one and see that these are very suitable models for energy absorption as a result of cyclic loading. Eurocode gives some guidelines now for fire safety behavior for different types of material. For example, the Eurocode number 2 gives a specific characteristic for concrete under compression and dependency of this same curve under compression of concrete for different temperatures. And this is automatically integrated in Diana. So the user can fill in the traditional diagrams of ambient influences of the characteristics of these curves by hand, just as diagrams for parameter value at certain temperatures. But you can also refer to Eurocode, for example, Eurocode number 2 or number 4, or full recovery. There's still a lot of discussion, and then it is not necessary to define these diagrams explicitly anymore because they are pre-coded in the Diana interface. And here you see how that looks like in the graphical user interface. And similar behavior is also defined for steel materials, as you see here. So user defines Young's modulus, some characteristics, and a class of temperature dependency, referring to code in to the Eurocode. A complete new material model that we offer in Diana 9.5 is the so-called modified to surface model, which is a model that is originally defined by Professor Usami in Japan and some of his associate professors. and colleagues. And this is a so-called plasticity model with two yield surfaces, in which the hardening of the concrete is dependent on the distance of the stress point from both yield surfaces. And this is a model that is pretty advanced for cyclic behavior of steel. It's available both for all type of material models, so varying from reinforcement bars or truss elements to full three-dimensional models or curved shell elements. A complete different class of material model that we offer newly in Diana 9.5 is a new liquefaction model. This is the UBC SAND model, which is developed by the University of British Columbia. That's where the name UBC comes from, which is available also in some other analysis programs, but the typical thing in Diana is that we have further developed this model so that it is suitable now for implicit integration schemes, so we can make rather large time steps or load increments, and it is also available in a three-dimensional formulation. And this is a complete soil model that is suitable for shear failure. It has a plastic cap also for nonlinear compression, and the hardening behavior is prepared for mixed isotropic kinematic hardening, so that we can simulate very nicely cyclic behavior up till onset of liquefaction, as is illustrated in the graphs here. But also the existing traditional models, as for example the modified Moore-Coulomb model, have been further improved. For example, the modified Moore-Coulomb model, we can ask the user to define a level of dependency on the power of stress. And we have modified the model in a way that if the user defines this parameter equal to 0, the exponential cap, hardening and elasticity are applied, and otherwise the power law cap, hardening and elasticity are applied. And this gives more robust behavior and also allows the applicability of the modified Moore-Coulomb model, for example, to slope type of structures where the sideward support to the soil is absent. So far in earlier versions there were sometimes convergence problems in these kind of situations, and this new formulation of this modified Moore-Coulomb model gives much more robust behavior. That's also because we extended this model with tension cutoff and the latency cutoff. And you can recognize the characteristics that need to be defined. For example, the latency cutoff defined by initial void ratio and maximum void ratio in the graphical user interface in the classes. For masonry, discrete masonry models in which all the individual bricks are modeled with continuum elements and the mortar with interface elements, we offer the COMBIF interface model, which is a combined characteristic of cracking, shearing and crushing. And we have revisited this model implementation and improved it such that also the stability of this model has been improved significantly in 9.5. Another approach for masonry models is the Rankine-Hill orthotropic plasticity model. This is more for the masonry structure that's modeled as a continuum, so not with the interface elements for the mortar. But masonry structures are in itself very anisotropic, and that's defined with this Rankine-Hill orthotropic plasticity model. The model originally was developed by Professor Lorenzo and some others, And recently this implementation was revised and modified by Van Meer, Lex van der Meer, who did his PhD at Eindhoven University and improved the stability of the model for stress conditions close to the apex or close to the point where different yield surfaces come together, and also the tangent formulation was been improved so that behavior is better for large strain increments. So far this Rankine-Hill orthotropic model was only available for plane stress elements, but we have extended the applicability now also to curved shell elements so that it can be used in three-dimensional surface models like you see here. When we look to new element types, there are not so many new element types coming available in Diana 9.5, but we have already many. But we have added in Diana 9.5 a new 3-node analytical integrated flat shell elements, which is an analytically integrated element. So we have only integration point in the plane of surfaces, and the relation is the constitutive model is defined in terms of in-plane strains, curvatures, and cross-section forces and bending moments. And this model can be used with the standard linear isotropic material definition or with linear orthotropic material definition, but it also offers possibilities for laminates, which gives different material properties defined in different layers. A new analysis module that we offer is the module for strength reduction analysis, which is called Reduct, from reduction analysis. And this is typical for geotechnical analysis, in which the user can assess the remaining capacity that's in the model before failure occurs. So many of these geotechnical models make use of frictionally dominated materials like more Coulomb type of material models, and the failure criterion is typically defined by a cohesion and a friction angle. And what we can calculate with this analysis is the reduction factor that can be applied to these properties, the cohesion and the friction angle, unless failure of the model occurs. So we reduce the failure criterion, as you see here, indicated originally by the black line, until it reached the critical stresses in the model and failure occurs. So let's look to some example of this. These are some benchmark tests. Here you see a slope, which is typical application for this kind of analysis with a user-defined cohesion and friction angle, and we reduce the cohesion and friction angle gradually until we have the factor that the stability of the slope is affected, and the slope comes down. What you see here is the displacement. You see very nice the soil sliding, and this is the equivalent total strain, in which you see the bending, the band, sliding band, in which the equivalent strains are maximum. And in this table you see some analytical results compared with Diana results and some other results, and that gives good agreement. This type of analysis can be applied both to two-dimensional problems as to three-dimensional models, as illustrated in this example. A major improvement in Diana 9.5 is also how to deal with the phased construction analysis. And we have modified this functionality in Diana so that in 9.5 not only the elements or reinforcements should be activated or deactivated, but also support sets or tying sets can be activated in the analysis command in a graphical interactive way. And this is very easy to do. The user can, in the new user interface, just select graphically the model components in the model tree, and with drag and drop switch them to or move them to the analysis control dialogs as you see here. But now we have also made possible that the user can define support sets in the user definition, in the model definition. He can activate in a phase 8 construction these sets. It is not necessary anymore to import or override support sets by importing external files anymore, such as was the case in earlier versions. We also have now the possibility that if certain elements are activated in a phase construction analysis, in this construction phase analysis you can, for the selected material of elements, define new material models. So going from one phase to another phase, we can change the material assignment in a graphical user interface now. What we see in this sheet is another extension of phase construction analysis, and that's the functionality in which in an excavation analysis the internal forces of the elements that are removed can be maintained in following phases. And this is very common functionality used in tunnel excavation analysis. We have made a function for automatically easy generating element loads and nodal loads for a pushover analysis. The user performs an eigenvalue analysis, selects an eigenmode, and can refer to that mode in the load definition in, for example, a nonlinear pushover analysis. A new procedure application is the vibration analysis module, which allows to do eigenvalue analysis considering geometrical nonlinear aspects. This was the PhD work of Tanvir Rahman, who is now one of our staffs, has done PhD work on this topic in Delft University, and this functionality is now available in Diana. Also, the calculation of Rayleigh damping parameters can be done now automatically in an eigenvalue module. So the user can define damping ratios for a certain minimum value and maximum value of a frequency range. The frequency range can be defined by minimum or maximum frequencies, or by mode numbers, or by minimum effective masses that should be considered in global X, Y, and Z directions. And then Diana automatically calculates the damping ratios, the damping values, damping parameters, the Rayleigh damping parameters, and applies these values. And this can be easily used in a nonlinear transient analysis, as you see here. By the following analysis sequence, the user says, okay, define the Rayleigh, calculate the Rayleigh parameters, do a nonlinear analysis with a certain number of time steps, and during these time steps damage is introduced in the model, so the stiffness is reduced of certain elements, and that means that also the Rayleigh parameters should be updated and modified. And after some time steps to be defined by the user, the Rayleigh parameters can automatically be calculated again and applied. So this is efficient procedure for updating your damping properties during your analysis. We have for tunnel analysis, tunnel lining analysis, with the casing being modeled with shell elements and the interfacing between the segments defined with the Janssen model. Now extended the output capabilities that not only the stresses and strains in the interface can be output, but also the cross-section forces and bending moments in the joints, as you see here. So here you see the cross-section forces and bending moments in the concrete shields segments, and here you can see cross-section relative displacements and forces or relative rotations and bending moments in the interfaces between the segments. We have made available the possibility to find complex loads. For example, if you have a large structure and you have an earthquake loading, you want to have the excitation on one part of the model, for example a column, in a bridge, be applied with an out of phase aspect for different piles, because it takes some time that the excitation moves from one pile to another pile. This can be defined by hand, but we can also define these frequency loading amplitudes with reference to Eurocode 8. For dynamic analysis in the hybrid frequency time domain application, we can offer now also the output, generate the output of the dynamic fluid pressures, how they act at certain time steps on the structure. Stop criteria in a nonlinear analysis so far were available only for element-related output results as stresses and strains, but can be defined now also for nodal results such as forces or accelerations or displacements. And user defines then a minimum value or a maximum value of a certain result in any element or node in the model, and the program automatically keeps track on this, continues until this limit value has been reached. Some more output items, for example, in a nonlinear analysis for interface elements, the stresses and strains, the tractions, can be checked against the Moore-Coulomb failure criterion. For example, with stress capacity results in which the shear capacity, which is defined as the ratio of the shear stress from a certain stress condition until the distance from the hydrostatic axis at the same hydrostatic stress to the yield surface, can be output. So if this is smaller than 1, we still have some capacity in the interface, but alternatively we can also use the hydrostatic pressure capacity. When this is equal to 0, the stress is on the yield surface, and when there is some stress pressure value remaining, we have some remaining stress capacity. Some more output results such as stress shear, which is giving the shear stress in the connection of a reinforcement bar and a motor element. Minimum and maximum result values are now also possible for potential flow analysis, heat flow analysis, or groundwater analysis. User-supplied subroutines can be defined and used as dynamic linked libraries, which gives much more flexibility with respect to the compilers that you can use. So far, we as software developers always wanted to use the most up-to-date compilers that are available, because that gives optimum performance for all our users, and we think that is very important. But for users who want to use user-supplied subroutines, this was not always convenient, because it forced them always, every new Diana version that we offer, to upgrade their compilers. And now we are much more flexible by offering these user-supplied subroutines as dynamic linked libraries. We have made some extensions on automatic tie-ins, some extensions in Euler stability analysis, but I think we'll If you want to know more about that, we can explain you that in separate sessions, or you can find that back in the release notes. Next category of new functionality is some specific new functionalities that we offer for the design engineer. And what we see more and more is that to checking designs of structures, that engineers want to use solid elements, because solid elements match very well with building information management approach, in which users want to use the real geometry, so as they defined in CAD geometries. But there are some problems. If you use solid models, then in the design of structures you need to do the calculation of cross-section forces and cross-section bending moments. In Diana we offer the functionality of composed surfaces for that, but so far in combination of solid element models, the composed element surfaces needed to be defined in a structured grid. And in Diana 9.5 we now offer the possibility that the user can define his reference surfaces with composed surfaces in an unstructured grid, and there is no relation anymore necessary between these unstructured composed surfaces in which we calculate the cross-section forces and bending moment, and the grid of solid elements in which the structure is defined, which gives a lot of more flexibility in doing design analysis with full three-dimensional geometries. Some more extensions, for example, for stiffness adaptation analysis, we can refer, same as for nonlinear analysis, now to all the design codes, and we have extended the design application, which the user can check according to the Eurocode number 2, whether there's enough reinforcement in the structure, also with checks for shear force and coverage. Here you see dialog for design analysis, in which the user can define and which output items he wants to check in the post-processor. In the same environment the user can define the load combinations. For geotechnical analysis, we say, and I explained in the introduction that we want to have more emphasis for specific features for structures and for geotechnical analysis. We made some modifications in Diana 9.5 that the user now defines on a model level the gravity acceleration and the gravity direction and fluid density. And this is important because in fluid structure interaction these parameters are required to convert the pressure heads into pore pressure loads in the structural analysis. If you still want to use an equivalent acceleration load, and so far this could be done by different weight loads, then we offer now the equivalent acceleration load in which a user can define explicitly direction number and an acceleration value, and these can be defined for different directions in different load cases. But other important extension in Diana for geotechnical analysis is that we now make possible that the user can output effective as well as total stresses as well as pore pressures in the soil, which you see, for example, in this result tree, with the E is the Cauchy effective stresses, the stresses between the grains of the soil, or the total stresses in which the contribution of the fluid in the grain, in the voids between the grain is added, and also the pore pressure can be output explicitly. So this is simply defined by following output items, stress effective and stress total, or the pore pressures. Also we have are offering now in Diana 9.5 some more functions in which the user can in an easy way, for example, define the relative conductivity as function of pressure head or the storativity. about commonly used functions. Last function that I will highlight here is the functionality of foundation piles. And in Diana we can define foundation piles as bond slip reinforcement, which optionally have an element tip in which the stiffness of the tip of the pile can be defined. And we have different functions for the characteristic material behavior for the pile shaft interface. As for example, the user can define an ultimate shear force per length, or he can define a diagram, but he can also define now newly a Coulomb friction model in which the stress normal to the soil is considered in calculating the maximal Coulomb friction model between the pile and the soil. And similar functions also available now for the pile tip behavior. And all these characteristics can be defined through these material dialogues. That brings me to the last topic of this presentation, which are the licensing options. As you know, in earlier Diana version, the licensing was restricted to hardware dongles. But with Diana 9.5 we will also offer the possibility of issuing soft key licenses. So users who prefer more flexibility, especially for your universities, this is a very pragmatic solution. We can offer next to hardware dongles also the option of software dongles. And very important is that with 9.5 we will also offer network licenses, which will allow you to use one license on different computer systems which are connected to your own network in your own organization. Of course, if you have only one license, you can only use this single license one at a time, but it is much easier, much more flexible to use one or a limited number of licenses on different sites within your same organization. This is an overview of all the new functionalities that you can expect in Diana 9.5. We hope that you will take this up soon and will be successful in using that. If there are any questions about issues that we have explained in this presentation, we can discuss this now. Otherwise, you're free to contact us after the seminar on another location before or after we have delivered Diana 9.5 to you. Thank you very much for your attention, and I hand over to Maas for some concluding remarks.